Thank you for coming. I am Mustafa Mohammed, and today I will be presenting to you our research on supporting students' meanings for quadratics, integrating RME, quantitative reasoning, and designing for abstraction.
So as we know, quadratic relationships are an important topic from middle school all throughout college. We build on prior work, which provides accounts of middle and high school students developing productive meanings for quadratic relationships via their quantitative and covariational reasoning. Whereas students in these studies leverage numeric quantitative reasoning, we are interested in designing a task sequence that supported them in both non-numeric and numeric reasoning to develop meanings for quadratic growth. In our study, our goal is to address the research question: how can middle school students leverage non-numeric and numeric quantitative and covariational reasoning to develop meanings for quadratic growth? Theoretical perspectives. Quantitative reasoning entails a student's constructed networks of quantities and quantitative relationships, and as I mentioned before, it involves both numerical and non-numerical reasoning. One of the key components of RME is that the tasks are experientially real situations. This could mean a dog race, or even a bacteria growing. In our situation, we provide students with an applet of a growing triangle along with 3D printed manipulatives to support the students in constructing amounts of change as a quantity unto itself, in hope that they would be able to identify a constant second difference. And we use these 3D manipulatives to support students and provide availability for abstraction through their sensory motor engagement. Our goal with the use of RME was to present this realistic situation to students in order to facilitate the reinvention of mathematics. In our research, the reinvention of models for quadratic relationships and potentially other types of relationships. Horizontal mathematization is a process of a student engaging in and developing understandings for constructed experientially real contexts. In our situation, we have the growing triangle. It is the way they informally symbolize, speak, and reason about the situation along with the 3D printed manipulatives. Via horizontal mathematization, students can begin the process of elaborating and extending those informal mathematical activity. This is referred to as vertical mathematization. This may include making a drawing, defining, or using conventional notations. Through this, the students reach higher levels of mathematics. In the process of both horizontal and vertical mathematization, the students construct new mathematics. This is called the process of progressive mathematization. Results should end with a shift from a model of a situation to a model for a mathematical idea. We conducted a teaching experiment situated in a whole class setting. It occurred in a diverse middle school located in the northeastern U.S. And class was selected from a convenience sample as we were invited by the 8th grade teacher. We taught 5 sections, approximately 76 minutes each, and covering the following topics. Our class consisted of 8 students, which we placed in 3 groups. 2 groups were audio and visually recorded. For brevity's sake, we focused this report on Neil, Aaron, and Nigel, one group that worked together throughout our 5 days. Afterwards, we conducted post-tests to examine the extent of their development of meaning for quadratic change. To analyze our data, we performed conceptual analysis. We analyzed all recordings. We were interested in examining the ways in which the interactions among the students, teachers, and the task supported students developing more sophisticated meanings for quadratic change. Results. Introducing the growing triangle task on day 3, we distributed the manipulatives to the class intending to support the students differentiating between the total area of the triangle and the changes in the area for each increase in the base length. To support students with meanings for area and the change in area, teacher-researcher engages students in the following conversation.
The different colors, right? So initially we have nothing, then it grows by this black amount. By the way, when we have nothing, what is the sideline? What is the area?
Zero.
Well, it's 0, right? Or you say they don't exist. Then we add 1 unit of side length, we get this much area. When I add another unit of side length, is the amount of area I'm going to add the same amount? More or less?
More.
It's more, right? So we're going to add on a little more. So when I add on another side length, what's going to happen to the area? More. Sorry, I dropped one. What's going to happen when I add another? More. Right? But what I want to make sure we don't lose is that throughout, I also want you to focus on just what the total area is. And that's why we printed out these gray ones. These are always showing us what the total area is. These other pieces are showing us the change in area.
Students were then asked to open up the applet on their laptops and begin making observations about the changes in the triangle. As they watched the applet, our students discussed how these changes were growing. As the students engaged in informal ways of speaking and reasoning about the situation, we then asked students to graph the situation. For brevity's sake, we do not present the students' initial activity for graphing situation, but they understood that for each time a new piece was being added to the triangle, the area being added was increasing by more each time. This could be seen in their graph as they have area on their y-axis, and for each change you can see their area increases by more each time. Whereas the focus of day 3 was on supporting students in identifying increasing amounts of change, on day 5 we returned to the triangle task with the intention of supporting students in imagining a constant second difference in this context. Because the students had already identified increasing amounts of change of area with respect to the side length, the teacher-researcher asked the students to consider how do the amounts of change compare to one another. They were asked to explore, and the following conversation ensued.
How do the amounts of change compare to one another?
So if we right? Oh, look, it's quadratic. Right, I can do it again. Same size. Let's put that one off. Same size. It's like this quadratic is going, I guess it's added onto them.
Neil here is characterizing the amount being added to each trapezoidal amount of change in the manipulatives as being equal. Without realizing, Neil is identifying this constant second difference non-numerically. So after identifying this constant second difference non-numerically, the teacher-researcher prompted the students to create a table of values as a way to normatively represent such a relationship. We are now transitioning from informal to more formal representations. Here the students are building a table of values.
How much was this one? Yeah, this was 5, right? So it's 5. 5 plus 4 is 9. But this one has to be 5.
Do that like that.
Right? Right, Juju? Yes. 1. We don't have 2. 3. 4.
Oh, that's it.
We don't have 2. So it's 5. 5.
5,
7. 7 plus 9.
So this piece is adding.
Here, Neil is identifying the area of the pink manipulative as having a quantity of 7. And knowing that, this new piece must be added to the previous total area to give us a new total area. So the 7 for the new piece plus the 9 for the previous total area, giving us a new total area of 16. To build on students' connection of the non-numeric constant second difference, we asked them how the values they had identified for the trapezoidal amounts of change manipulatives, these first differences, and the difference in these second differences to be shown in their table.
I forget what this much is. This
Just
is
say
right?
yourself.
Yeah. We're trying to figure out how the amounts of change are changing. Right? So this is how the areas are changing. The amounts of change are getting bigger. Right? So that's the thing
What? 2. Oh! Yo!
It's adding 2, right?
That's 2.
And then you
You smart cookie.
How'd you figure that out? I wouldn't know that off the top.
We infer here Aaron was connecting their informal identification of the constant second difference with the manipulatives to the changes in these amounts of change represented in their table to identify that the constant second difference has a value of 2. Extending their model of the growing triangle task to a more general model for constant amounts of change, we provide students with a new task, asking students to find new points along the table, knowing that there are constant second difference within the situation presented. The following conversation ensued.
The difference between the plus 1 and plus 2 is plus 1. That's constant.
Aaron here was able to find that the second quantity, the plus 1 and plus 2, to find the constant second difference of a value of plus 1. Using that, he realized the next first difference had a value of plus 3 to find his new volume value of 8. Nigel engaged in a compatible activity, finding the second difference value in order to complete the table to find new points. We infer that the students leveraged a meaning for constant amounts of change to calculate the values of the new points within the given relationship. The shift to a model for a constant second difference. After engaging in this activity, we introduced the definition of quadratic growth to extend students' understanding of a relationship that contains a constant second difference as a quadratic. Although students had learned about quadratics previously, there was no evidence they connected this constant second difference to their activity with quadratics prior to our giving this definition. Finally, we ended the sessions with a post-test. We present the data of two tables shown with options linear, quadratic, cubic, or exponential. Given the first table on the left, Neil and Aaron found the constant second difference and identified the relationship as cubic, whereas Nigel successfully found a constant second difference value of 6 shown in the image. He continued to find a constant third difference of 0, and he concluded that the relationship was cubic. One possible explanation is that he may have not noticed that the constant second difference was similar. On the right side, all three students were able to conjecture that this was a cubic relationship. We highlight how we were able to draw on these theories to support students building models for quadratic growth. Designing for mathematical abstraction supported us in developing manipulatives we conjectured could support students in constructing the following quantities. The manipulative supported students in both numeric and non-numeric quantitative and covariational reasoning, as well as their engagement in the mental actions described by Carlson. Designing the task sequence with RME principles supported the shifts in the students' meanings for quadratic relationships. Connecting RME to the other theories, we note how the 3D printed manipulatives were critical to the students as they transitioned to vertical mathematization, as they were able to identify this constant second difference. We highlight how students leveraged their quantitative and covariational reasoning as they moved from models of the growing triangle task to models for constant amounts of change to further models for quadratic growth. We conjecture integrating activities like these to support students in developing more productive meanings for amounts of change and quadratic growth. We call on researchers to explore how to support larger populations of middle school students in leveraging non-numeric and numeric quantitative and covariational reasoning to develop important mathematical ideas for quadratic and cubic and others potentially. Thank you.